Okay, we're going to advance our investigation into the Frobenius method today by looking at these equations. So these are differential equations that fit into this form. X squared y double prime plus x p y prime plus q y equals 0, where p and q are both functions of x. Many of the equations will come in this form already. If they're not, then you'll divide through by the coefficient of y double prime if it's not an x squared, and you'll multiply through by any number of x's necessary to put that x squared coefficient there. Once it's in this form, you can basically pull out the functions p and q and then evaluate them at 0. Well, once you've evaluated p and q at 0, you're going to then solve the following quadratic equation: r times r minus 1 plus p naught r plus q naught equals 0. This quadratic will have two roots, and the nature of those roots is then going to determine kind of the method that we will use to approach solving the Frobenius equation. And there's three possibilities we're going to look at. In case 1, basically the difference between the two roots is a non-integer. So r1, r2 differ by a non-integer. And if that's the case, then this is case 1. And the approach on case 1 is to first assume that y1, the first solution to the differential equation, is going to be x to the r1 times the series solution we've been using all along, the power series centered at 0, n equals 0 to infinity of a n x to the n. So in essence, you'll be subbing in x to the n plus whatever r1 is, the first root of the indicial equation, and then you'll try for your second solution just the second root. So it will be x to the r2, and then that's going to be summation n equals 0 to infinity of bn x to the n. Because there doesn't necessarily need to be a relationship between the a's and the b's, and this will give you two linearly independent solutions. Of course, our hope, once we find the recursive relationship, is that this turns out to be some series that has a definition like e to the x, or sine, or cosine. But that doesn't necessarily have to happen, right? Case 1 is the simplest of all because you'll be able to find both solutions by doing just a series substitution and following through on the method of the Frobenius that we've been looking at for the last couple of days. It can get a little hairy working with the indices, but at least these are relatively straightforward in terms of the substitutions. You're not going to use anything other than the Frobenius substitution, all right? So that takes care of case 1. Case 2 and 3 are slightly different. The good news is solution 1 for each one of them is always the same. Case 2 is when r1 is equal to r2. When you get a double root, then basically this is case 2. In case 2, your first substitution, so you're going to go r1, and that's equal to x to the r times the standard series, n equals 0 to infinity, a n x to the n. And again, you'll be looking for the coefficients a that build this series solution. So that's your first guess. And in essence, it means that when it's a double root, you treat it just like case 1 in the first scenario, right? The second one comes as a result of, remember, we kind of introduced these with the idea that these were a lot like Euler-Cauchy equations. And of course, whenever we had a double root with an Euler-Cauchy, the first solution was x to the m, and the second one was x to the m times the natural log of x. And so it shouldn't come as a big surprise that y2 is equal to whatever your y1 solution is times the ln of x. And then, of course, you need a series for the additional coefficients that might come out of it. So it's x to the r summation n equals 0 to infinity of bn x to the n. Now, we're going to hold off on this until our next class period. So any of the problems that you're assigned to do tonight that are case 2, we're just going to focus on the first solution because we're going to talk about ways to reduce the work for the second one. There are times when substituting this in is not convenient because, again, this solution for y1 may in fact be an infinite series that doesn't resolve itself into a single function, in which case its derivatives include large indices. So that's the reason why case 2, finding the second solution, can sometimes be a little tricky. Another option for these is not to use this formula for case 2, but instead to go back to what we learned in chapter 2, section 1, which is to reduce the order of the equation and to solve it with an integration factor. Consequently, one of the things we're going to do tomorrow is review integration factors. Okay, so again, that takes care of case 2, and for tonight, you're just going to focus on finding the first solution in case 2, and you're going to hold off on the second solution. The last one then is case 3. And case 3 occurs when R1 and R2, differ by an integer. When R1 and 2 differ by an integer, we'll use another technique. It'll look very similar to when they're a double root. The first equation, again, I'll sound like a broken record, is x to the r1. And one thing about these, there's definitely a relationship between them. R1 is bigger than R2, so R1 is larger than R2. So when you have two roots and they differ by an integer, there's definitely a priority. The larger of the two roots is always R1, so that's the one that's used for the first solution. And that's x to the r1 summation n equals 0 to infinity of a n x to the n. The second solution to this one looks a lot like the second solution to case 2. Let me label this. This is case 3. The second solution to case 3 looks a lot like the second solution to case 2, with one fundamental difference, and that is y2 is equal to k y1 ln of x. And it's possible that k could turn out to be 0, which means it's possible that you get two solutions to this that look very much like the two solutions to case 1. So case 3 can sometimes default to case 1, and there are even times when both solutions come out of your y1, so that you might not even need to try the second one. And then, of course, the rest is the same. This will be x to the r2 summation n equals 0 to infinity of bn x to the n. Once again, for tonight, I want you to hold off on these. I'd like you to just basically take any of the three cases and solve for the first solution. You can go ahead and do the second solution of case 1 because it's just a repetition of the same process. The only difference is you're going to use an r that's different, which means it's going to change the power on x for the series that you substitute in. But other than that, basically all case 1 problems are like doing the same substitution twice with just the difference of the exponent on x, okay? But these, for case 2 and 3, the second solution is fundamentally more complex, and we're going to look at some alternatives to that. That'll be tomorrow's class, is ways in which we can reduce the work for case 2 and 3, finding the second independent solution, all right? So that's it on case 1, 2, and 3 and how you're going to approach them. In my next video, I'm going to do a couple of example problems. Again, it doesn't really matter which case because for solution 1, it's the same substitution in every case. So I just want to model a few of these for you so you can see some of the various ways in which we work with these series in terms of reducing indexes and ensuring the powers of x match up so that we can look at the various ways in which the recursive relationships come out. All right? So watch the follow-up videos to get good examples.